Welcome, everyone. Thank you for being here. My name is Juan Pe. I'm a consultant, an independent consultant, also now the CTO of a very young startup called Bronze. And I've been working for many years in the fields of music, graphics, film, robotics, a lot of things that have to do with real-time systems, very interactive systems. And this is why I've become preoccupied and very interested in persistent data structures. When we talk about persistent data structures, we're talking about data structures where values persist after modification, right? We don't mean here maybe the usual sensing when we talk about persistence, like saving things to disk, even though we will come back to that later. What we mean is this notion of values persist after modification. One easy way to achieve this is via immutable data structures. If the value can change, the value naturally persists. So I'm going to be talking actually about a library that already exists, which is called Immer, that I've actually presented here in previous instances. So let's see how this thing works, right? Like, what do I mean an immutable data structure? Because this is counterintuitive. The whole point of a data structure is that it changes over time, right? So what the fuck are you talking about, Juanpe? So we mean that we can change the data structure, but we change the data structure not by mutating the value, right? Instead, we change the data structure by producing a new value with the contents of the data structure changed, right? So we see here that we have a vector A, and we introduce a new element in the data structure, and what we get is a new vector B with that element added. The value A persists, and that's what we mean by persistence in the context of this talk, right? One nice property of this is that you can use the data structure even if it's const, right? Because you get new values, you don't mutate the existing value. So you can do all sorts of things with this. You can, set a new value to manipulate an element at a random index in the vector and do a lot of things with this. So one naive way to implement such a data structure will be with something like this, where to implement the Immer vector, we just have a mutable vector inside, and then we implement immutable versions of the pushback and set methods. And here, I'm just actually showing off one nice feature of C++23, where we can actually explicitly mark the this argument of a function. And by doing this, in this case, we're doing this to be able to receive the this argument, right, the thing that goes before the dot when you call a method, by value, right, which is not something, it's something that you couldn't do before C++20. You will have to write this method a few times, once for const references, another one for move, for R value references, and whatnot. So here we get the this value, or the this, argument by value. We can modify it locally and return using C++ nice value semantics of values, return a copy of the whole thing, right? We can do the same thing for set, and we're done. Of course, we're not done. This is the beginning of the talk, because this will be very inefficient, right? You can think of, we will be copying large vectors of data. Any algorithm will explode into quadratic behavior. This is not what we want, right? So how do we implement an immutable vector in a way that is efficient? And the problem was, as I was saying, that the problem with a standard vector is that a standard vector implements the data structure using an array, right? An array is a contiguous block of memory, and that's actually why we love the standard vector. It's very efficient because of this very contiguous arrangement of data. But this means that if you want to modify the data, but persist the previous value, you need to copy the whole data, right? So if we want to set something at a random index 10, we need to make a copy of the whole thing. So we solved this problem by slicing up the data into smaller chunks. So instead of having a big block, a big array, we have smaller arrays that are arranged together in a tree fashion, right? In this way, if I want to modify an element of this tree, I can just modify the place, in this case the index 10, I can modify the place, the block where that element is contained, and then of course I need to also copy the other internal nodes that refer in that path, right? What's nice about this is that we get a property that we call structural sharing. What this means is that when you have different values that are derived from one another, right? Like I have a value A, a data structure A, and then I modify modify the element at index 9. These two values, A and B, even though from a programmer's point of view they're completely independent, they work like copies, internally they share structure, right? They share data, and that's why it doesn't blow up your memory usage, it doesn't blow up your algorithmic complexity. There is this structural sharing property. And this is a very important property that we will come back to a few times in this talk. If you want some more technicisms, the name of this data structure is called a radix balanced tree because it's actually a perfectly balanced tree. And it's actually like a sort of form of prefix tree with an I, with a very wide branching factor. I was using a branching factor of 4, so the blocks were of 4 elements in the slide. This is just to make the slides a bit easier to see. We can build this data structure with any branching factor that is actually a power of 2. Because we actually in practice going to use very wide branching factors, branching factors of 32, meaning like every node, every inner node, every leaf nodes, they have 32 elements. A lot of the algorithms on this data structure, we call them effective O1. This is a little bit controversial. Some people say, oh, that's bullshit. I'm not the first person that started making this claim. This was actually made by Rich Hickey, who is the inventor of the language closure, who is actually the first person that he didn't invent this data structure, but he popularized it because he made the very bold decision to make this the default data structure to implement the standard vector type that you get in Closure. It's implemented using this, right? And he says, well, if you have a branching factor of 32, right, you're going to be able to, like, with just 7 elements deep, you're going to be able to have a vector that doesn't even fit in any computer memory that you could ever have, right? So if you're kind of physically bounded by 7 levels, is that 7 a constant, or is it like, your algorithmic complexity growth? So I think, it's an interesting way to look at this. You can think, like, for example, random access on this vector, you can see it's effective O1, of course, with a non-trivial constant, right? Particularly when you're modifying it because you need to allocate nodes, etc. But this is, one of the claims that we can sometimes make about this tree. But what's nice about this tree is that it's also very cache efficient because even though it's like a node-based data structure, it's like a tree, the blocks are big, right? Which means you have actually a few cache lines on every node. And this means that actually when you iterate over it, random access, that's not going to be the case because you still have to sometimes like chase things. But when you iterate linearly over the thing, performance is really comparable to an STD vector. Like I have benchmarks to prove this. Then there is another variation of this data structure that is actually implemented in Immer, which is the relaxed RB, where like the structure just changes a little bit. I think there are other talks of mine where I explain that if you're interested. But with this new data structure, you also have logarithmic time, and this time real logarithmic time, not effective O1 time, concatenation. And also slicing, which means that you also get logarithmic time insertion at any point. This is something that you don't get with standard vectors, right? And this opens the door for all kinds of interesting algorithms, particularly in the context of parallel algorithms, because you can, for example, do a parallelized filtering algorithm, because you can like filter in parallel on all the vectors and then concatenate the results. What's interesting also about this data structure is that some operations like pushing back at the end is not amortized O1, it's actually real O1. So for example, what I mean by this is with a standard vector, when you're pushing at the end, it's most of the time constant, but when you're unlucky, you need to copy the whole vector, right? This doesn't happen here because it's a tree data structure. You're always like pushing back small blocks of data. So for a whole family of algorithms, this is an interesting property to have. We can also, with similar strategies of having like wide node data structures, build, also based on powers of 2, build hash table-like things. So we don't only have vectors, we also have unordered maps and unordered sets. and something I call table. You can look it up on the documentation. That has similar properties. It's characterized by a branching factor of 32. Also, because there is no rehashing, there is like a constant-ish latency, which is interesting for a lot of algorithms. It's very compact. It's actually more compact than an ordered map. There was a project actually with Facebook where they replaced the use of an ordered map by Immer maps with the original goal of actually reducing the latency of a lot of operations and their throughput. Both actually they managed thanks to avoiding lots of locking when reading the data structures, thanks to the immutability property. But a nice property was also that memory usage was reduced by half in the program. So this is really nice, and I think what's interesting about these data structures is not only kind of the gritty little details of how they're made, but actually the new architectures that they enable. I think they enable us to write our programs in a different way that I like to call value semantics at scale, right? Because they really allow us to work by value and think by value for big data structures, for big document models, and to really reshape our data structures and our software architecture, thinking in a value-oriented way first. What do I mean by this? Well, there are, I think, three things that these data structures bring to the table. One is lots of advantages for concurrent programming, and this is probably the most obvious one. No? If you have a mutable data structure, let's say we have a document, and this document, is built of vectors and maps and whatnot, and we want to save it to disk in a separate thread while the user may still be interacting with the application and changing the document. We need to have some kind of mutex, right, to make sure that nobody is modifying the document while we're actually reading it during the saving operation. This means that we actually lose a lot of what we may want from concurrency, right? Because while we're actually saving, the user may get like a spinning wheel if they try to change anything in the document, right? If we're using immutable data structure, the code becomes way simpler. Because the data structure is immutable, it's actually almost trivially copyable. There is also like a reference count that you need to touch. But you can just capture this document by value, right? You can capture it by value. You have your independent copy. You don't need to use any lock. You can just save it to disk in your own thread safely, no headache, and higher performance, particularly from the point of view of the user, that it's not going to see any spinning wheel or any latency issues when interacting with this. A less obvious property of these data structures is that it allows us to reason about change. What do I mean by this? In a lot of software, particularly the kind of software that I work on very often, like what we're trying to do is like we have a model, some kind of document, and the user is interacting with it via actions and producing new documents, right? Producing a change to the document. Now, a lot of the job of the programmer is trying to figure out what changed in this document so that we can update other systems, for example, the UI, the visual representation of that document. And if you think about it, in a mutable place, this is actually a difficult thing to do. And the way we often do this is we have the document, and because the values don't persist, right, you actually don't have a way to programmatically analyze the document and figure out what changed. What you're going to do instead is the programmer is going to be disciplined enough to add different callbacks, right, to inform that the change is happening as it's happening, right? So other parts of the program can, connect callbacks here to, let's say, there is a foo property and a bar property. They have an associated callback to know that it's changed, right? So the thing is now you cannot just modify the attribute, right? You need to have some kind of dropper function that is also going to call the callback under the hood. But this has a few problems. One of the major problems that I find is that this strategy doesn't really compose. So if you have an operation that does change both bar and foo, right? You're not getting a notification for I did my complex operation. You're getting individual notifications for foo and for bar as they change, right? This means that you may even see broken invariants. Let's say that bar has to always be greater than 42. The user here in line in the set foo line, it's actually going to see a broken invariant inside the callback, right? There are all kinds of problems opening by this approach. And nonetheless, callbacks lead to callback hell, and we have the spaghetti code monster that eventually takes over our code. So what happens when we're using value semantics? If we're using value semantics, things compose naturally. First, you don't need to have, hide every modification behind a method just so you get the callback. You can just modify the thing. And here in complex operation, this is composing, right? Because from the point of view of the user of this function, they pass a value and they get a value. What happens inside the function, they don't see it. They don't know. They don't know that it's first modifying foo, and they don't know that it's then modifying var. They just know that there was a document and now there is another document. Yeah. Now, because there was a document and there is another document now, and the two values, they are there for you, you can inspect the changes and try to compare things to figure out what information, what I care about, what actually did change, right? One interesting thing is that this is enabled also by the property of structural sharing. The structural sharing means that if the vector didn't change, or they change just a little bit, this comparison is going to be very fast, right? It's not going to go through every element of the vector trying to figure out if it's the same or not. If the two things are the same, the pointers are going to be the same. It's going to say, well, it's the same, right? Another cool thing that you can do with this data structure, this is actually a property of the maps and the sets, is that you can even diff them. And you can diff them in a time that is proportional to the amount of change, not proportional to the size of the data structure. So if I have a value A and then I do some changes, I can call this diff function that is going to compare the value A and B and tell me what changed. And because of the structural sharing, it's not going to have to go through the whole tree, because as soon as it sees like a subtree that is the same pointer, it can say the whole data that is here didn't change, right? So this is really, really handy when writing particularly interactive software, software with UIs, but all kinds of things actually come up once you get used to having these patterns in your code. The other thing that you can do with this is time travel. And one classic example where we need time travel in our applications is when implementing an undo history, right? The classic way of implementing an undo history in an object-oriented way, this comes from all the way back to the Gang of 4 book on design patterns, is you write a command pattern, right? Where for every action in your application, you have this object that represents the change and that implements it in two directions. You have a do method that implements it forward and an undo method that implements it backward. And you hope that you implement it correctly and you did the right inverse of the function in the undo. And then, you implement this, have lots of implementations of this for every command. I mean, this works and has been used in many software, but there are some disadvantages. One of them is that you need to make sure that undo is actually the proper inverse of do. The other problem is that actually you cannot really jump around. If you want to jump 10 steps back, you need to undo every intermediate step in between, right? If we're using immutable data structure, another way to implement this is to say, I have a vector here is an Immer vector, right? Well, actually here it doesn't matter whether it's an Immer vector or not, because the vectors that we're interested in, they are inside the document. We have a collection, anyway, whatever data structure you use of documents, that represents the document at every stage of your undo history. And maybe you have an index telling you what's the current position in the undo history where you are. And that's it. That's the only thing you need. Like every time you're just presenting a different document to the user, you don't care about how the document was produced, how you did it or how you undid it. You just have a document. And this is not science fiction. This works. It has been used in many projects. And I think actually what people like the most in my talks is always the demo. Sometimes now I showed like a crazy text editor. Today I want to show a project I've been working on for a few years. It's a piece of music software on a company I'm the CTO of called Bronze. where we're making a system to make music where the music is nonlinear, has a nonlinear structure, so that whenever you play it back, it can play a new thing. You get a new performance of the music. So this requires a very highly dynamic system, and that's why we decided to use these techniques and technologies to implement it. So I'm going to show it a little bit to show you that, you know, this thing works. A lot of people think, oh, but there is a lot of data being copied. You have all these nodes. It's inefficient. I think I can show you. Let me see, because I'm in a different window manager that I am normally. If I can. And now, okay, actually now it would be handy to mirror, or maybe I just look like this. So here we have the software, and if I open a document, we see, you know, everything loads in the background very quickly, and it has this timeline that is actually being generated out of this nonlinear structure that I have here. That actually represents the music piece that I have. So every note here is a section of the piece, and this is a Markov chain that describes the actual structure of the song. So I can play something back. It picks up somewhere in the middle, and it's choosing out of all these sounds that are being laid out here, it's choosing some of the sounds to play and some to not play using probabilistic rules. It's probably too short time that I have to really explain how all of this works. I just wanted to show you that this can work very efficiently. And for example, I can even like clear the timeline and generate a new timeline very easily, where it's kind of picking sections from this graph and really making a new piece. And this piece, I can really just go around, you know, select hundreds or even thousands of things in it, move them around. And I can also go in the undo history and like move and see, and hear automatically what the document was at that point in history, right? I can also, click on it. If I just hover it, it just presents it to the user. If I click on it, I actually move there. And because it's playing back, it added new sections. But yeah, anyway, I don't know how long this is now. I cannot see very well. Should have. This is 10 minutes long. It's not even that long. You can actually generate it. I think there is a loop now. The loop off. I'll press clear instead because I cannot see properly from here, you know. Anyway, I think it's kind of nice. It's also a kind of a show-off. But it's a talk, so I guess I'm meant to be showing off what I'm working on, right? Anyway, I'm just trying to convince the hardcore C++ developer this works, right? It's efficient. It's not going to make your program run slowly. If anything, it's going to actually make it run faster, right? Let's go back to the talk. Let's see if I can close this. The music, by the way, it's music by Arka. It's one of my favorite artists, and she's done a few projects with us. So yeah, you can go on our website later and listen more of this piece. Which is a bronze rearrangement of her piece Rikiki. That's one of her albums. Okay, close without saving. And let's go back to the talk. Okay, this was all really fun, but we're only halfway through the talk, right? So there must be some problems here. No? There must be some challenges. It's not all utopia here. Ominous music. Tension. We get to the second part of the talk, persisting persistence. First, small disclaimer for educational purposes. When I say vector in the next slides, I mean an Immer vector with a branching factor of 1. Right? This actually turns the vector effectively in a binary tree. This can be configured in the templates that are provided by the library, which sometimes allow you to optimize depending on your architecture, your system, or your use case, how wide you want the nodes. In this case, it's useful to have smaller nodes so we can see the tree in in the slides. Okay, so we talked about the undo history, and we talked about how that was enabled by the structural sharing, right? Because normally if you have like an undo history where you copy all the documents in your history just grows very fast because you have lots of copies there. But this was enabled by the fact that we had the structural sharing. The document did only contain, or these different copies of the document did only contain new data for the differences within these trees. Now, all of this happens in memory, right? What happens if we try to serialize to disk our immutable data structure? Perhaps because we want to have the history saved to disk to have something like infinite undo, where you're not constrained by the memory that you have in your computer. This is less and less of a problem these days, but software that implements infinite undo histories, they normally have persisting the history to disk. A trivial-ish, naive-ish way to do this will be to do something like what I'm going to present here. So we have the document, and we use a library like this library that I use in most of my projects, actually called Serial, that gives a serialization to JSON and to other document formats, where we implement serialization by kind of just instructing the library how to traverse our data structure or how to traverse our document, right? In this case, we get an archive that can be any kind of archive. It could be a JSON archive, an XML archive. We get our document and we say, well, our document has a member data, so go with the archive into the member data, and we use this MVP thing to give it a name. So if you're using a text format, you see the string data associated to that thing. Then we can implement this also for Immer collections. So we can use loading, where we just iterate over the data that's contained in the archive, loading elements one at a time. Here I can show an interesting property of the data structures also. There is a move in this line before pushing back into the value. And this move here is actually relevant because what we're telling the compiler here is actually that the variable m, we don't care about the previous value. We don't want to persist that value, right? M can be given and consumed by the pushback function, which is going to return a new value that we're actually going to store straight away into the variable m. That's why we don't care about the variable m. No, we're in a loop here, just pushing stuff back. Thanks to this move, the pushback function of the Immer vector can optimize things and actually mutate the internal tree often, giving us, in this loop, actually performance that is kind of equivalent to filling up a standard vector. Thanks to the fact that, yeah, we're not having to allocate new nodes in the tree most of the time. We can just modify the nodes that are already there. Then we have the save function, where similarly, we're going to here store the size. In the previous one, no, we had to load the site first and then iterate loading all these elements. Here we do the opposite. We store the size first, and then we iterate storing every element. Here again, there is something to show that is interesting about the library. We use Immer for each instead of a standard for loop. The reason is that Immer for each can be more efficient than using iterators. And the reason for this is because Immer for each can do what we call internal iteration. So it means that it goes through the tree, recurring in the tree, calling the callback as it traverses the tree, right? It doesn't return control to you for you to be kind of pulling things from the iterator. If you use an iterator when using a tree-like data structure, the iterator needs to contain a kind of stack, right? To kind of know where in the tree you are, right? So this Immer for each is marginally more efficient. If you use Immer for each, actually you get performance comparable to iterating over a standard vector. You don't always have to use it. To be honest, a lot of the time I just use iterators because they're convenient at the place. But if you want maximum performance, you can use this function from the library. Anyway, so now we can, once we have this, we can finally save our document to disk or to a string or whatever. Here, for illustration purposes, we create a first vector, v1, that has 4 strings. Then we add 2 more strings to it. And then we had a third vector that is actually identical to the second one. Then we create this history, which is a vector of documents, and each document just had one vector, right? Just to remember in the previous slide, the document is just one Immer vector, right? Just for illustration purposes, it's a little bit of a dumb document, but it's what you get in slideware. And then we serialize this document. Oh, sorry, this history of documents. And what we get is an array of documents where each document contains the array of data, right? But what we see here is that we lost the structural sharing, right? Because we had our beautiful tree. If we represent the three values that we were trying to save to disk, they actually are just this tree. There could be a forest. In this case, actually, there is they're more like a tree or a forest also if you consider the V1 kind of being off the tree. Instead of structural sharing, each string actually appears only once in this tree. When we save it to disk, though, they're treated independently. So they're stored as arrays, as JSON arrays, independently. So if we load this back to memory, when loading it back, we don't have information anymore about how these individual strings were arranged in blocks together, right? So what we get is actually three different independent trees, right? We lost the structural sharing. So this is not good. We're a little bit sad now. What do we do now? Okay, so the solution that we propose today is to think of this forest of trees as one thing. We call this thing a pool. It's a pool of data structure. It's a pool of values, right? Now, if we consider the pool as one thing, we can serialize the internal structure of that pool because we're not considering V1, V2, V3 as independent things. We're considering the whole set of data structures that we want to store as one thing. We serialize to disk. Now, when loading, we will deserialize the pool, and out of the pool, we will extract the individual data structures, preserving the internal structure that they had before they serialized. So we've actually implemented this, and this is what we're presenting today. It's a new experimental library that is provided inside the Immer library itself, called Immer Persist, that finally allows us to persist the persistent data structures. How does this work? Sorry, someone was taking a picture. Did I ruin your picture? It's all right. So we have our document, and the first thing that we're going to do here is to add some way to introspect the document at compile time. For this, we use BooShana. BooShana is a metaprogramming library for C++, probably some of you know it. And with this macro, we tell BooShana what the shape of this struct is, so that at compile time, we can actually do some kind of poor man's reflection. If we had C++ 26, we could use the very nice new reflection mechanisms because I'm dealing with older systems. I use this. You could actually even use Boost Fusion, which is even more old school, to do this. I think in C++ 20, you could also use Boost PRF, which is a bit hacky, but it will do the trick as well. There are different ways to do this. I'm just going to present this one. Once we have this, actually, already a nice thing is that we don't need to tell serial how to serialize each of our data structures. If our data structures are already lifted inside BooShana, we can use BooShana to tell serial how to serialize any data structure that is BooShana compatible. And we do it like this. We have a serialize function that constrains our value for being a BooShana struct. And we use BooShana for each to iterate over the members of the struct and serialize that into the archive. That's pretty neat. Once we have this, we have our three vectors from the previous slide. We have the history with these three vectors. And when we're going to serialize it, we're not going to call serial directly. We're going to use this function called serial save with pools. We tell it what kind of archive to use, what kind of place to put it in. We pass it the history. We pass it this policy that I'm going to tell you later what it means. And what we get is this. Now, this is a little bit of a mouthful. It's actually more text than it was before. You can imagine that this scales better than the other one. But what's important here is that when you look at the value that we actually were serializing, the data is not put there directly, right? The data is just an index to something. And you can already see that the second and third vectors, which were the same, they have the same index because it's the same data, right? We already know this. And where does the data live? The data live in a pool. So this serializes all the pools in this block. And for each container that you have in your document, or each container type is going to create a block where it's going to serialize all the internal nodes of the data structure in there. So data was a vector, an Immer vector, right? So you get here, it serializes the constants that were used to build the vector tree. And you can see that there are 3 leaf nodes, which were the 3 leaf nodes that we were seeing in that tree data structure. There is node application, right? The strings, every string appears only once. Then there is 2 distinct vectors, right? Because V2 and V3 were the same. There are 2 distinct roots, right? Two distinct vectors. And then there is a couple of other inner nodes, right? So, I mean, this is like a moving target. This is a very verbose way to serialize this. We could probably have a less verbose way to do this. I think for a slide it's still okay to have maybe this little bit more verbose representation. But what's interesting is that even though it's verbose from the syntax point of view, from the complexity point of view, what I mean is a spatial complexity, we get the structural sharing in here. As you add documents and documents, this is not going to blow up in size. And when you load it back, you're going to preserve the properties that you had before you serialized it. So you get the structural sharing property transferring across sessions of your program, right? I passed that policy, and the policy controls things about how those pools are built. Because actually, what's nice about the library is that, I mean, there are a few ways in which you can use it, but what's nice about the library is that, I didn't show this fully, but the library here in the document, we only have one vector. But the library can actually see all the data structures, and that's why we're using Bushana, all the data structures that you have in your document tree, and figure out all the containers that are the same. So, for example, if you have vectors of ints in different parts of the tree, it's going to serialize them in the same pool, because there could be potential structural sharing even within one instance of the document. And it's going to aggregate them and produce these pool types, right? So there are different decisions that you could make about these pool types, and that's why you have this policy where you can decide, for example, well, first you can tell it which pool types do I want, right? And actually, if you use this, I think you can even get away with not using Bushana at all, and you just tell it, okay, I have a vector of int and I have a vector of strings, and this is what I have in my document. Then for each data structure, you have to give it a name. By default, the other one was picking the name of the first attribute that mentions that type. That's why it was called data, because the attribute was called data. But you can just give it whatever name you want. And then you can also customize how you actually save and load the root value. So this way you can give it a different name. By default, it was producing this value 0. That's kind of a behavior that actually comes from serial. With this, you can just give it a different name, for example, history. Okay, that was probably almost too much detail. We're going to talk about another use case of this library that I think makes it quite interesting. Because we were talking about how, okay, we can take the pool, we can save it, and then we can load it. This transformation that is happening here, the saving and loading, it could be an arbitrary transformation that we're doing here, right? we could be interested in producing anything. For example, transforming the elements of the strings. Now, we had strings in the document, maybe we want to make them uppercase. If we do this in the trivial way, we will have something like a transform Immer function, where you just use std transform, and you use this thing called transient to give it a mutable API, so you have it a bit more compatible with the standard algorithms, like back inserter here. And then I transform v1, v2, v3, producing x1, x2, and x3. Right? If we do this, we get the same problem, x1, x2, and x3, because they were seen as independent values from the point of view of the code. Now they don't share structure anymore. Right? We destroyed the structural sharing here. Because in every of these transform Immer calls, we went through all the elements of that vector from the point of view of the external API. We didn't go through the nodes. We went through the elements, right, producing a new vector. What we want is to preserve the structural sharing, right? We want to get the same pool transformed with the uppercase values in it. We can use Immer Persist for that. So here, one use case that actually comes from the Bronze code base, which is actually what motivated a lot of this work. It was actually our use in Bronze that motivated the implementation of Immer Persist. Let's say we have the document that we have that was vectors of strings, and we're going to put this in the namespace v1, because now for v2 of our software, we want to change the document and be just a vector of chars, because we realized we were always using one element strings, so we can get away with just having chars, right? Now, what we need to do is to transform, if we load a document that was done with v1, we will need to transform it to v2 to upgrade the document and to have compatibility with older versions of the software. Again, we inform Booz HANA about the shape of these structs, so we can get a little bit of magic. And the way we're going to implement this is we're going to make a HANA map where for every container in the document, we're going to say how we want to transform it. So in this case, we say for every vector of strings, we want to transform it with this transformation. And the transformation happens on an elements level, right? So it happens on the strings that are getting transformed into cars. Because the structure, what we want is the algorithm, the system, to iterate over the structure, producing the same structure, while we tell it how to transform the individual elements that are contained within the structure, right? So in this case, because we're transforming, these strings, we're going to just pick the first element of the string. If the string was empty, we just put a null character. So, here a little bit more detail of how, for this is a Booz HANA map where it's a compile time map that associates for each type. It tells it, in this case, for example, for the type vector of strings, it tells it what the function associated to that vector is. So now if we want to transform our documents, because we want to upgrade them, let's say I have this history, and the history is composed of all documents, of v1 documents. What we're going to do is that we're going to get some pools out of the history, and we have this distinction between input pool and output pools. This is an output pool because we want to extract things from it, right? We want to extract values out of the pool, and we're going to transform the pool using the transformation that I just showed before, right? This transformation map. Now we can go through the history, and for every document, we can call convert container, which is part of Immer Persist, where we pass it the old pool, the new pool, and the data that we're interested in at this point, and it will produce the transformation in a structural sharing way, right? So You need to pass the two things because it will actually P1 you can see is mutable because in the transform pool it will actually lazily transform the documents as it sees, and it will see which nodes are already transformed, which are not, and do all the tricky things that you need to do this efficiently, and provide you values that preserve the internal structure. So now we can finally get our history of upgraded documents with the history preserved. So actually, if I do this and then I serialize the documents after all of this, what I will get is something like this, which is basically an identical document, except in the leaf nodes, instead of having strings, I have characters, which are serialized in JSON as the code of the character. So, we're getting close to the end. More interesting things about Immer Persist. I was always talking about hash tables here. Sorry, about vectors and linear sequences. The associative containers also work. So hash tables and sets, they work. They have array map trees based data structures. There is some things to consider though. The first one is that if you're going to use the documents, for example, if this is a document format that you're going to use across systems, right? You need to use a portable hashing function for serialization because the results of the hashing function are going to be relevant for the structure that is produced. So you need to make sure basically the hashing function becomes part of your format, right? We provide a wrapper for XXHash that you can use directly with the library. You can use other ones if you want, but definitely std hash will not be good in this case. Also, another thing is converting between key types is supported, but you have to be careful, right? Because you have to make sure that the key types that you produce have the same hash than the ones you had. Otherwise, you're basically producing a corrupted tree. But this is useful if you use, like, for example, we do actually use like type safe IDs. So we have like ID types that are internally like a UID, but we don't use just a string. We use like a type-safe way of doing this, no? Where and sometimes between versions of the document, you need to upgrade from the old type to the new type, and this is supported. There are more use cases for that. Also, as mentioned, complex data models work. So I was showing a document that has just one data structure in it, one vector, but you can have any number of vectors, any number of hash tables. All the things that have the same type can be combined into the same pool. A lot of it happens automatically. Also, recursive data models work. This was important for us because we're actually working on a new feature where like every sound in the timeline can have a whole timeline in it, and this happens recursively. Yeah, this was a little bit tricky to get right because you can imagine like as you load something of that type, you still are kind of building the pool for that type and whatnot. But this is working actually. So you can have vectors. You can have, let's say, a document of vectors of documents, and this will work. This is still a work in progress. I said it's kind of experimental-ish. We're starting to use it in production, but we haven't released actually any version of the software with this running. And there are also a few to-do things that we want to do. One is incremental processing. So I was saving documents in one block. One very interesting thing will be to produce the pool one step at a time. And the undo use case will be a very good example for that, right? Where you probably don't want to just save the undo at once. Maybe you want to save the undo, when you're closing the application so you have it the next time. But maybe instead what you want to do is like whenever you do an action in the application, you want to save the document associated to that action, right? And to save the document associated to that action, you will serialize the differences between everything that you saved before and this document, right? So you will save like a partial pool with only the differences here, and then when loading, you will kind of combine these pools so you can read this document. I think this is kind of, very plausible with this approach, but it's a feature that we haven't implemented yet. We don't have an API for this. Binary formats is also something that we haven't implemented yet. We were using JSON because we were using JSON in our application, so that was our first thing. XML, we tried it in unit tests and it's working, but binary formats are not, and it would be very useful. Also for having a more compact representation, I was showing how it was a bit wordy. You see inner, reflects, blah, blah, and a lot of those words could be skipped to get something that is a little bit more wordy, less wordy on disk. Another interesting thing would be to maybe make the library be serial independent. There is a couple of places where actually it assumes that you're using serial, and that serial is the way you're persisting things. I don't think there is something fundamental in the approach that will require this, right? So it would be nice to be able to pass serial as a sort of policy, and if you are using a different serialization library, you can hook into that. Particularly, I think a lot of like C++ libraries these days use a similar approach to what serial does, right? So if you use, I don't know, boost serialization will be the old school one that uses a similar approach. Also, build time and object size, I think, could be improved a little bit, because now, you know, for every type, you get a whole serialization of the pool independently. I think we could use a little bit of type erasure in the implementation to get build times and object size better. I also really want to thank Alex Chabalin. He actually implemented most of this, so I'm the one presenting this, but he sadly couldn't come to the conference. And yeah, he's an excellent developer. He's also an independent consultant and freelancer. He's been working with Bronze for a few years. So if you need a top C++ developer on your projects as a contractor, I will definitely recommend you to hire Alex. He's a wonderful developer and person. So we're wrapping up now. Just one last slide with the key takeaways here. If there is anything that I want you to remember from this talk, the first one is structural sharing, right? The structural sharing is this property of immutable data structures that enable value semantics at scale. It's the thing that, allows many values that you treat independently from the point of view of the interface, which is very useful as a programmer, right? Because independence gives us concurrency, gives us all these nice things. Internally, they are not independent, and that's what gives us the performance, which is what we also want as programmers. And to be able to get this structural sharing property across sessions of our program, right? Across transformations of a data structure. When serializing the data structures, we can use this new library, Immer Persist, that I presented today, and I hope you find use if your projects, if you're interested in immutable data structures. Finally, also help us. As I said, it's work in progress. There is a big to-do list. A lot of this work has been sponsored by Bronze, but we're also like a very small startup, also currently looking for investment. If any of you are using immutable data structures at work or is interested in using them, contributions of any kind, whether in code or in money or whatever, are always useful, right? So yeah, help us make this library better if you want. Some last pointers of previous talks. You can probably see this afterwards. Oh, what is this? New Firefox features. Where you can dive deeper into the data structures themselves. That's the first talk, into the design philosophy behind this kind of architectures. What I was talking about value semantics at scale, that's the most valuable values talk, or the squaring the circle talk, which is interesting if you're considering of integrating this approach in a more in a software that is already using a more object-oriented approach in a lot of the code. I think this talk can help you maybe bridge the gap. Thank you a lot. Thank you for listening. And if there are any questions, I hope we have a couple of minutes for that. Thank you very much. Perfect.
Go back to slide 34.
34. You have very good eyes, because can anybody else see the 34?
Yeah, it's called taking a picture and zooming in.
A high-resolution camera. Escape. Oh, well. Yeah. I'm just anyway. I'm just gonna do it in the manual way because why is it moving back and forth now?
One more.
Okay, here.
Okay. So you have that move in a loop,
Yeah.
meaning you move the vector repeatedly.
Yes.
Normally, this would be an anti-pattern, a dangerous thing to do, and I don't know what static checkers will have to say about this.
So there is some discussion about what happens when you assign to a moved from value, right? Some people that are very strict says you cannot make any assumptions about M, so you cannot even make the assumption that you can assign to it. I personally find that too restrictive, and that's why Immer guarantees that you can assign to M to restore kind of a valid value. So what's happening here is that, so when M that is moved here is consumed by pushback, right? It becomes a moved from value, right? You cannot operate with it and you cannot do anything with it. But the next thing that we do is assign to it, and we're restoring a correct value into it, right? A valid value. And that's why this pattern does work in Immer. I mean, if you don't like it, or you were saying your code sanitizers are going to complain about this, you can use the transient, which is that API I showed in some of the other slides, where you get like a mutable interface for your data structure. And you can also use that to achieve the same level of performance. I use this because, I'm used to...
Yeah, actually, I didn't notice the self-assignment. I do wonder if this, though, is stable enough. I mean, what if you forget to do the assignment?
If you forget to do the assignment, then this code is incorrect because you're moving into pushback. But actually, you're going to get a compilation error because pushback has no discard marked on the result. So if, you're going to get a compiler error telling you, hey, you need to use the result of pushback, right?
Yeah, otherwise but you could assign to something else.
If you assign it to something else, then that would be a problem, If you're, in this case, Okay. Any other questions?
Time for one more, I think.
Maybe on the same slide, why don't you return by value?
Sorry, why do I?
In load, instead of having an out parameter in load, return.
Why do I? Because load is from serial, right? I didn't design this API. This is what serial is going to use to learn how to serialize. Yeah, if I had designed the API, I probably would return by value.
That makes sense.
Sorry, one last comment for those people who don't speak German. Immer is German for always.
Yes, correct. Yeah, thank you. I don't know if there was one last question there, or?
The document reference on the left should probably be named data, right?
Can you repeat the question?
On the left, the reference to document, the document ref.
Yes.
The same name twice.
Probably
data, right?
So he's asking whether the document reference on the left should be data.
It's just the name.
The name. The name of the variable should be data. That's correct. Yeah. Yeah, that's a typo. I clearly didn't compile this code. Yes, thank you. It's a very public code review. No more time for questions. Thank you very much again. I'll be around for this.